Welcome to the final unit of Geography 105, Weather, Climate, and You. This is Unit 17, focusing on remote sensing and forecasting of our atmosphere. And if you just take the first piece of what we're really going to be examining today, we'll be looking at various ways where we observe Earth's atmosphere and then use that information to help make a forecast. So if you've ever looked at your mobile device or internet webpage and tried to figure out tomorrow's forecast or a forecast for next week, a lot of that hinges on the ability to be able to sense what's going on right now in the atmosphere, and we call that remote sensing. And then we basically feed that data into a computer model that can then help develop a forecast. And there's various ways to make forecasts, and we'll talk about those in this lecture. But one of the main ones used today is numerical weather prediction, where you essentially mimic the atmosphere inside of a computer. And so we'll take a look at that as well. The picture here in the center is of the WSR-88D NEXRAD radar. We have several of these around the United States, and I'll show you show you that distribution here in just a second. But these radars are vital to our ability to detect and forecast specifically precipitation, but they can also help us develop rotation or detect rotation inside of storms. And so obviously that's important for precursors of what we discussed in the severe weather lecture. So let's jump right in here. The definition of remote sensing is really just the science of being able to obtain information about something without actually being in contact with it. So right now you are remote sensing this lecture by listening to the words that are coming out of your audio speakers. You're remote sensing with your eyes. You're reading the information from the slide. And so we could say that's remote sensing as well. Remote sensing is done along something known as the electromagnetic spectrum, which ranges from very small wavelength rays like gamma and X-rays. So you can see the units here in terms of meters, 10 to the minus 10th meter, so very, very small wavelengths. The wavelength is really just the distance in between these waves, so from crest to crest or from trough to trough. You then get, as you get longer wavelengths, you get towards the visible portion of the spectrum, which we discussed in the energy lecture, so 0.4 to 0.7 microns, and then all the way up the wavelength. So what we talked about in energy and heat and this idea of the electromagnetic spectrum is very relevant here in terms of our ability to remote sense. Some remote sensing is active, meaning it sends out electromagnetic pulses. So things like radar are electromagnetic active remote sensing platforms. Others are passive. So they essentially listen or wait to try to receive electromagnetic energy from some other source. Satellites are generally passive remote sensors, and I'll show you what those look like in just a second. Okay, so we'll start with really the first and arguably the most important for precipitation detection, at least, and that's weather radar. So if you've ever turned on the news and seen the greens and yellows and reds moving across the map, those are images of Doppler radar. And radar is actually an acronym for radio detection and ranging. This is really a World War II technology that was used to track enemy aircraft. And it found out that just so happened it was also very good at detecting precipitation inside of weather systems. And so now Doppler radar is widely used across the world to detect precipitation and to track movement of precipitation. There's also been an upgrade to the Doppler radar network that you may have heard called the dual polarization capabilities, where the radar basically sends out a vertical pulse and it also sends out a horizontal pulse. And then it can basically measure the aspect ratio of raindrops. So you get a pulse through the vertical, you get a pulse through the horizontal, you can then tell the shape of the hydrometeor or the precipitation droplet that you are hitting with the radar. So that's a relatively new capability of the Doppler radar network in the United States that is very helpful for determining what type of precipitation is falling. So is it rain, is it snow, is it hail, etc. So here's the spatial distribution across the United States of the Doppler radar network. You'll see close to home here in Chicago, we do have a radar out near Romeoville on the campus of Lewis University. That's the Chicago 88D. The next closest would be up in Milwaukee. We have one out in the Quad Cities and down near Springfield, Illinois at the Lincoln National Weather Service office. You can see they're widely scattered around the U.S. and the reason for that, why not just put one giant radar in Kansas and have it send out energy and detect precipitation systems? Well, the problem there is the Earth is curved, right? So if you were to put a giant radar in Kansas and send out pulses of information, by the time it got to Colorado or Nevada, the beam would be so far above the surface of the Earth that you wouldn't be even detecting the precipitation. So we have to strategically place these around the country at various intervals to be able to have beams that are close enough to the surface to observe the precipitation actually falling and making it to the surface. You'll see we do have some pretty big gaps in the 88D network. Those are areas where it's sort of difficult sometimes to detect rotation in storms or what types of precipitation is falling. And then of course out in the Intermountain West and the Appalachia area, we also have issues of beam blocking, where mountains are in the way, and when you send a radar pulse, you can't see what's going on beyond the mountain range. And so we do have beam blockage issues in the West and also in other mountainous areas. But in general, we have, in the central 2/3 of the United States, you have really good radar coverage. And so this really helps us detect these precipitation networks. Canada has their own network as well. It's much more sparsely distributed than the United States, and places like China and Mexico also have radar networks, although they're not as robust as the network that we have in the United States. So how does NextRad work? Essentially, a pulse of information is sent out and it hits a hydrometeor, whether that's an ice crystal or a rain droplet. Some of that radiation is returned, so it hits just perfect tangent of the raindrop or the snowflake and is returned. And the power returned, by the way, is much less than the power sent out because it's being scattered in all directions. But some of that power is being returned back to the radar, and then we can tell basically, depending on how much power is returned back to the radar, we get an idea of how intense the rainfall is that the radar is hitting. Now, this radiation pulse travels at the speed of light, so we know the speed of light is a constant, and we can basically tell how long it takes to get there and back, and that gives us some idea of whether or not the storm is moving towards us, moving away from us, and really how far away it is. So the Doppler radar principle to be able to detect whether or not the storm is moving towards you or away from you is very simple, actually. You've heard this before. If you've ever watched an IndyCar race and you've ever watched a car go by, you sort of hear sound that is like, nee, nee, right? You can tell the difference in the pitch of the way, whether or not the race car is coming towards you or moving away from you. And so when the storm is moving toward the radar, we get an increase in the frequency of the wave, so a shortening of the wavelength. In other words, the radar sends out a pulse, and the one that comes back is of a much greater wavelength. If the storm or the object is moving away from the radar, that same pulse will be sent out, but when it comes back, it will be of a much longer wavelength than the one that was sent out. And so the radar basically just listens for that wavelength shift, and then it can tell whether or not the storm or the object is moving toward or away from the radar. This is basically developed, this is what we call the Doppler effect or the Doppler shift. This radar, or having these radars across the country, which were the network that is in right now was installed mostly in the early 1990s. This has improved the detection of rotation in storms, so this has improved tornado forecasting. Doppler radar can identify rotation in a storm, but not necessarily the tornado. So if you hear a tornado warning, Doppler radar indicated, that means the Doppler radar is detecting rotation in the storm. The radar can't actually detect the tornado itself, really for two reasons. Number one, the tornado is below the beam height, and number two, the actual resolution of the radar is not adequate to be actually detect and stratify that these small tornadoes are happening within the storm. So in a nutshell, Doppler radar has been a very good thing for severe weather forecasting over the last 20 years. This is what a supercell thunderstorm looks like on a two-dimensional planar view, so a bird's eye view of Doppler radar. You can actually see the supercell structure, so forecasters would very much be looking for that hook at the southwest side of the storm. And this particular storm, you can see the very high reflectivities in here, 65, 70, 75 dBz. This particular storm was producing a softball-sized hail as it moved across portions of western Iowa. So no doubt a forecaster could use this information and draw some warning polygons out ahead of the storm to alert people in its path that they might be experiencing severe weather in the next 20 to 30 minutes. So again, one of the major things that forecasters look for with supercells, as we discussed in the severe weather lecture, is the presence of this hook echo or pendant on the southwest side of the storm. The tornado would be located inside the hook pendant. Now, in conjunction with that reflectivity image, the reflectivity is basically how intense the precipitation is, or how much power is being returned to the radar, where the darker reds indicate greater amounts of power being returned to the radar, so basically heavier precipitation in the reds and the yellows. They can also use the velocity image. So sometimes in the news, if you're looking at in a severe weather situation, the meteorologist on TV might pull up one of these velocity images that are basically looking for areas of red and green that are very close together, or what we call couplets. So the way to read these velocity images is fairly simple. You figure out where the radar is in this image. So is it over here? Is it over there? Is it over to the right? Where is the radar? So you can see the little arrow here. I put the radar is up here, maybe at location X. And anywhere in the red, the wind is basically going away from the radar. Okay, so the first thing you do is kind of draw these arrows where it's red, the air is moving away from the radar. Wherever it's green, the air is coming into the radar. Okay, so this would basically be, you could kind of see the difference. There's some sort of boundary or front here. That's probably outflow from the storm. And anywhere else you have green, right, the air is coming into the storm. So right away, you can visually see an area that would be very interesting here, where we have strong outflow and strong inflow. That's really what we call gate to gate, or right next to one another. So that area circled in, let me clean that up here, this area circled in the yellow would be a Doppler radar signature of strong rotation in a storm that might lead a forecaster to issue a tornado warning. So we look for those outflows and we look for those inflows right next to one another. That may be a sign that a tornado is present. And you guys will have some opportunities to do this in the e-investigations manual to take a look at these inflow, outflow, and Doppler radar signatures of severe convective storms. Is everything you see on radar actually weather? The answer is no. Not only does the radar pick up precipitation, it also picks up birds, bugs, insects, things that, large explosions, sunrises and sunsets when the radiation from the sun is looking directly into the beam. So here's some examples of non-meteorological scatterers. Over on the right, you can see a band of precipitation on the radar. This is actually precipitation showing up here. But then you see a whole host of these other non-meteorological artifacts, these little, they're like little pulses, if you will, that are coming from different radars. So 7, 6, 5, 4, 3, these are all locations of radars across the country. You can see these little pulses that are all pointing in the same direction. This is actually when the sun sets and the radar looks exactly into the sun, you can get these pulses of radiation that show up as false echoes. So these are sunsets detected by the Doppler radar network. You can also see ground clutter here at locations 3, 4. There's some ground clutter here. There's some ground clutter in Oklahoma. These are essentially locations where very, very close to the radar, where the radar is picking up leaves, birds, perhaps insects, things that are non-meteorological scatterers. All right, let's switch from radar to satellite imagery, because there's some brand new satellites that are coming online now that via NOAA that are really revolutionizing the way we view the atmosphere and view Earth from space. So satellite imagery comes from two types of satellites. You either have a polar orbiting satellite, which we call POES. These polar orbiting satellites are just that. They orbit around the north and south poles. So as the Earth rotates, these orbiters are basically going from North Pole to South Pole and around the Earth that way. Now that's unique because that allows for full coverage. So in other words, that satellite will fly over Chicago, that satellite will fly over London, that satellite will fly over Sydney, Australia, but it's never over the same place all the time. And so it's very useful for full disk, what we call full disk coverage, to be able to see everywhere across the globe. But it doesn't allow us to actually focus on one particular place and watch cloud patterns evolve. In order to do that, we have to have geostationary satellites. So the GEOG platform. The nice part about the GEOG platform is as the Earth rotates, these satellites also rotate at the same rate. So they're basically at a fixed location in the sky, and in the example here shown in the bottom right, if the satellite was in this location, it might be able to, constantly view the continent of Africa. It'll always have pictures day and night as it's fixated over the same point. So this geosynchronous, or what we call geostationary orbit, is basically an orbit that is fast enough that it catches up and maintains the same rotation rate as the Earth, and so it's always at a fixed point. We have two satellites that monitor North and South America that are provided by NOAA. One is GEOG West, the other is GEOG East. These geosynchronous orbiting satellites essentially provide great coverage of the Western Hemisphere, and we use them every day for tracking things like hurricanes, mid-latitude cyclones, cloud features, weather patterns, you name it. These satellites are a fantastic tool in order to be able to monitor what's going on. So I'm going to pull up in another tab here, and then I'll bring it over some satellite imagery of just basically today, so you can get an idea of what this looks like. So I'm going to pull up some full disk. We'll go to the full disk imagery so you can see what that looks like. And let's see if I can just go ahead and do a true color. And we'll go ahead and animate this so you can get an idea of what this looks like. So this is the brand new GEOG 16 satellite. GEOG 17 has also been launched and is in the testing phases right now. Depending on when you watch this video, it might actually be operational. But this is basically a true color image. In other words, if you were sitting on the International Space Station looking down on Earth, this is exactly what you see. Notice that during sunrise here, North and South America appear dark because there's no sunlight. So this is a passive sensor that uses visible light from the sun in order to illuminate its passive electromagnetic sensor. So we're looking at roughly it depends. This is roughly around this is a blended channel between 2, 4, and 7 microns, where we can actually get different portions, or 0.4, 0.6, and 0.2 microns, where we're basically blending a bunch of spectrums in order to get an idea of what this would look like from the naked eye from space. And then again, you can see, right, we can track large cloud patterns, we can see the ITCZ very well, we can see these large mid-latitude cyclones that are traversing across the CONUS. So it allows us, these satellites are really invaluable when it comes to tracking weather systems in real time. And you can certainly get very high level views of this. So let's just go, let's see if we can go zoom way in and get some satellite imagery. So I'm going to go ahead, and if this participates well, this is, by the way, if you're interested in this is through the College of DuPage website. They have a pretty good website for satellite viewing. I'm going to do a local sector here. So I'll just go pick something where there's some interesting weather today, and then loop this for you so you can see. So this is the visible channel, just looking at cloud patterns. You can actually see mountain waves going. So as air goes over the mountains, the Appalachian Mountains, it creates these little ripples and waves. So pretty cool to see that. You can go to a true color to see what it would look like with your naked eye. You can look at different regions. So lots of different stuff that you can do with these satellites. Very cool. You can even see some thunderstorms developing across southern Kansas and Oklahoma on this day. So depending on the day, there's always something cool to look at on satellite imagery, and it allows meteorologists to observe what is happening right now, which is really vital, as we'll see, to making a forecast. The GEOG imagery that we'll typically use as a forecaster, which you'll see in your weather studies manual, is the visible, infrared, and water vapor channels. So this is essentially going from shortest wavelength to longest wavelength, where the water vapor channel is around 7.6 microns. The visible channel, as you know, is 0.4 to 0.7, and the infrared being in between those, where we're really just sensing different portions of the electromagnetic spectrum. They're all used for different purposes. Visible is very good during the day when you have sunlight. Infrared can be used at night when there's no sunlight, but you're detecting cloud top temperatures. And water vapor is just that. It's a certain portion of the electromagnetic spectrum that's very responsive to water in the gaseous phase. And so as that energy, what the satellite is essentially doing is detecting energy emitted at the 7.6 micron wavelength, and then we find that that's a very good proxy for where water vapor is located. So here's a couple examples of all of these. Visible, again, only available during the day. You can see on this particular satellite image we have a nice big low pressure system counterclockwise swirl over the Gulf of Mexico. You can see all the clouds here across portions of the southeast. We might have some sort of frontal system draped through the upper Midwest. Pretty clear over Kansas, Oklahoma, and Texas. So, this is really a meteorologist's best friend in terms of detecting weather patterns on any given day. Here's an example in the lower right of some overshooting tops of supercell thunderstorms across Arkansas. And these are actually, we found through research, pretty good at detecting where the strongest storms are and where the storms that are most likely to produce tornadoes and hail are located. So forecasters will even sometimes use satellite to try to detect if a storm system is gaining strength, losing strength, or perhaps maintaining strength. So very useful, the visible channel. But when the sun sets, we don't have visible anymore, and so we have to use infrared. This is like putting on a pair of infrared goggles, or if you've ever seen those police helicopters that chase people at night and look through thermal imaging, that's kind of the same thing that's going on here from satellite. The infrared satellite is detecting really temperature of the first object that it hits. So if it hits the ground, it's of course going to be much warmer. If it's sensing a cloud before it hits the surface, of course those are going to be much colder. So here's a great example of some clouds over Wyoming and Colorado. We have some deeper convection, some deeper thunderstorm activity over Texas and over Oklahoma. And so the infrared is very useful at night when we don't have the visible channels to be able to look at. And then finally, water vapor. Since water vapor is such a big component of our forecast and our weather system, it's a very important greenhouse gas, as we mentioned. Water vapor can be proxied here at the 7.6 micron wavelength, where we're really just looking for large amounts of water vapor content. So you can see this area that I basically have outlined would be areas of large water vapor content. You'll probably find clouds in those locations. And then areas where the atmosphere is very dry and does not have a lot of water vapor. So portions in this image of Mexico and Texas and Oklahoma where not a lot of water vapor is showing up. And of course, water vapor is very important, right? It's a variable gas. It's an important greenhouse gas, and tells you something about the availability of moisture for precipitation. So another very important channel that meteorologists tend to look at is this water vapor channel. We also have other observing platforms that are sort of, a little bit different, but very important. You can imagine for for detecting thunderstorms and their movement, we have a lightning detection network that actually detects the strikes of lightning and thunderstorm activity across the world. This is not just the United States. We actually have this capability over the globe. And now we actually have lightning detection that is possible from satellite. So the satellites in geosynchronous orbit can actually now have sensors on them that are sensitive enough to actually detect lightning strikes even during the daytime, which is very impressive. So these lightning detection networks are spread around the world. Here's just a view of the United States. And what essentially here happens is, let's say there's a lightning strike across, let's just say eastern Kansas. And what will essentially happen is a bunch of stations will kind of detect that strike through electromagnetic sensing. They will triangulate and pinpoint exactly where that strike was located. That data will then be radioed back to a satellite that then goes to a ground station, and then this ground station collects all that data and information and then can plot where lightning strikes are happening over the United States and over the world. So very useful for meteorologists that are watching thunderstorms evolve, right? Because as one really good proxy for how strong a storm is how much lightning it's producing. And so meteorologists can track and watch that with these lightning detection networks. Okay, so we gathered some data, right? So we've remotely sensed the atmosphere. Step two is, once we make this diagnosis, is really to make a forecast. So given that we see something on radar, given that we see something on satellite, given that the lightning detection network has picked up this feature, how do we then make a forecast? And this is a really interesting and challenging topic because it involves different timescales, right? Are you making a forecast for tomorrow? Are you making a forecast for next week? Are you making a forecast for next month? Right? So these different timescales create different challenges in terms of what we are able and not able to do in regards to forecasting the atmosphere. Generally, what meteorologists are doing in order to make forecasts are really looking for significant features that would cause the weather to change on any given day. In other words, what would be present in the atmosphere that would cause a sharp drop in temperature? Maybe a front, right? What would cause the wind speed to change direction or to change strength? Maybe the movement of a cyclone through an area, right? So we're looking for significant features both at the surface and in the upper levels to give us clues as to how the forecast might change over the next 24 to 48 hours. That really involves different methods. Okay, so I have them listed here, and just for your reference, as we go down the list, the skill, so how, in other words, how good the forecast is, at least at short terms, increases as we go down this list. So in other words, a climatological forecast would be the least skillful forecast. Persistence would be better than climatology, analog would be better than persistence, and NWP would be better than analog. So the forecast essentially gets more skillful or better as we go down this list. So let's talk about each of these different methods. The first is climatological forecast. This is based on long-term averaging. So in other words, what is today's average high temperature in Chicago? Right? How would you find that? You'd go back through the last 30 years worth of data. You'd find the high temperature for today's date. You'd average all those values, and there's your climatological forecast, right? The average high in August in Chicago is 86. Right? So the forecast for today then would be 86. Now, you can imagine climatology is probably not going to be right all the time. In fact, it's very rarely correct. It can be correct, but it's very rarely correct, right? It could actually be 85 degrees in Chicago today, but more likely it would be less than 85 or more than 85 rather than being right at 85. So these climatological forecasts give you sort of some boundaries as to what to expect for any given location at any given time of the year. An example of a climatological forecast would be the probability of having a white Christmas, right? So you take a bunch of years of data, you figure out how many years out of that sample has snow on the ground for your given location. You then calculate a probability. So let's say half of them, right? Out of all this entire sample, half of the years have snow on the ground during Christmas. And so the areas in the yellow here represent a coin flip chance of having snow on the ground at Christmas. You have other locations that are 90 to 100%, right? Would be the forecast for having snow on the ground at Christmas. So those types of forecasts are essentially just averaging historical weather conditions. The next, and a little bit more skillful than climatology, would be persistence. Ben Franklin was really the first to identify persistence and try to forecast using persistence. This is the idea of essentially linear extrapolation. So let's say we have a cold front across the Great Plains. Yesterday it moved 800 miles, and we would then forecast today it to move another 800 miles, right? Well, it just so happens that our atmosphere is not linear, right? It's a very chaotic and dynamic system, and so linear extrapolation breaks down, especially on the longer timescales. The persistence forecast and linear extrapolation works very good on short timescales. In other words, there's a storm moving towards DeKalb. 10 minutes ago, it was moving this far. We would expect it to go this far in the next 10 minutes. that's a really skillful forecast because of the very short time scale. As you go into longer time scales, so get into days and certainly into the weeks time frame, persistence really begins to drop off in terms of skill because our atmosphere does not behave in a linear fashion. The analog method now getting a little bit more skillful than persistence. This is basically forecasting what's going to happen today or next week or next year based on past scenarios with similar conditions. So the analog method is like a giant game of matching, right? So you've ever played the memory game before where you flip over those little cards, right? And you got to find the same match in the deck of cards. The problem with the analog method, though, as you'll see if you ever dive into this method, is that no two memory cards are ever the same. So maybe you flip over one card, right? It has Mickey Mouse. You flip over the next card, it is Mickey Mouse, but it has Mickey Mouse with half an ear missing. And so this creates some challenges. No two weather patterns are ever the same, and thus we can't expect that either of those outcomes would be exactly the same. They might be very similar, but they're likely not to be exactly the same. The other problem with the analog method is that you're relying on past scenarios. And so what happens if what you're about to experience has never happened before? In other words, you flip over a card, it's Mickey Mouse, and you search through your entire deck of cards and you don't have anything that even resembles a mouse, right? That creates a large issue. You're basically in uncharted waters for your forecast because you've never had a past scenario that has had anything close to what you're about to forecast or what you're about to experience. And unfortunately, those are the forecasts that you want to get right because those are probably the extreme forecasts that the public is really relying on you to get correct. And finally, NWP, which uses computer programs to mimic the behavior of the atmosphere. This is really where our science of weather prediction analysis and forecasting has gone in the last 20 years. We now use computers to simulate the behavior of the atmosphere using some state variables, winds, pressure, temperature, humidity, etc. And in these, the denominator is always time, all right? So DT, as you go into the future, how does temperature change, right? Is temperature going up? Is it going down at this location, or is it staying the same? And so these computer models are incredibly sophisticated, and they take the input from our remote sensing platforms and they simulate them going forward in time. So this is kind of what this looks like. We break up the Earth into these theoretical volumes or boxes of air. We then assign temperature, pressure, humidity, wind speed, wind direction to each of these points through our remote sensing platforms. That data then goes into a computer program, in this case supercomputers, because we're solving information at lots of different grid points, and they all interact with one another. These programs then output things like temperature, precipitation, wind speed, wind direction forecasts for generally out to 2 weeks, although some models go out beyond that, which I'll show you in a little bit. There's a whole host of statistics that can be done on these, and so I put this down here in the bottom, MOS, which is basically for every given point, we can do some bias correction and some statistical sampling on this output to make the forecast better. So these short-term forecasts are really getting very good on any given day. You know, most forecasts are within 2 to 3 degrees for temperature, and forecasts for precipitation, especially outside of the warm season, which involves thunderstorms. If you're outside of that season, the forecasts for precipitation are actually very, very skillful as well. We do have some issues when we get into the summer because of the very small grid spacings of our models, that thunderstorms just inherently in the summertime are a little bit harder to predict because of their scale. If you're going beyond 72 hours, so a couple of days, you're going to probably use this technique known as ensemble forecasting. And if you're familiar with the term ensemble, so an ensemble in music is just a bunch of different instruments playing together. Ensembles in weather forecasting use output from several different models to try to make an envelope prediction of what's possible. In other words, if you're looking at a graph and the x-axis is time, so going out in the future to the right, and temperature is on the y, all right, so this is your temperature forecast. What we try to do here is we have one model predict what's going to happen out a few days, so maybe 4 to 5 days. We have another model that's initiated with slightly different conditions, try to forecast what's going to happen, and another model, right? And so what we end up getting then is this nice sort of envelope, right, of what's possible out into the future. And this gives us or allows us to assign some probabilities to the forecast. In other words, the probability of achieving freezing temperatures in Chicago is this percentage. And it's a much better way to represent the uncertainty in our atmosphere. And so we use these things called spaghetti plots or spaghetti diagrams to help us understand the uncertainty in the forecast as we move on. And so I will actually go back to the College of DuPage site here and show you what those ensemble products look like. So here's one of the basically flagship NOAA model, the GFS ensemble. What we can do here is look at a spaghetti plot. And so for purposes of this discussion, just imagine that these lines are representing the location of the jet stream, okay? So at time t equals 6, so 6 hours from now, right, you can see there's very good agreement between all of the different members in the ensemble of where the jet stream will be located. If we go out a little bit into the future, so 180 hours from now, you'll notice that there's still a pretty good representation of where the jet stream will be located, although the spread among the members is starting to increase. And so the uncertainty in the forecast is starting to increase as we go out into the future. And finally, 2 weeks from now, you can see that the spaghetti is everywhere, right? It looks like a bowl of noodles. And this basically represents extremely low confidence in the forecast as to what the weather pattern will be looking like as we get into the 2 to 3 week time period. So you can see, right, how the solutions diverge away as we go into the future, and that's because of chaos theory. Chaos theory is essentially the idea that very small changes in the initial condition fields can cause large differences as we get out in time. So the errors begin to square and square and square, and they become so large beyond 2 weeks that the forecasts basically become useless. So then you ask, well, if we have very little skill forecasting beyond a week, then how do we forecast what it's going to be like this winter? How do we forecast what the temperature is going to be like in the year 2100? Those involve not using numerical weather prediction. They use different methods to try to forecast what's going to happen. And because of the chaos theory examples, we can't generally use numerical weather prediction beyond 2 weeks. And so we use other ways to do this. And that brings me to long-range forecast. So long-range forecast is the idea of predicting weather for 1 month or beyond. What we're really doing here is blending NWP output and forecasts of statistical analogs. So we leverage statistical dynamical framework to be able to forecast what's going to happen months from now. We try to use teleconnections like ENSO and sea surface temperatures, snow cover, and other variables that we've found to be skillful at identifying certain weather regimes to be able to help us forecast what may happen as we go into the next couple of months. But I just wanted to mention these because you will see these, right? The NOAA winter outlook, the NOAA summer outlook. Where are those coming from? Those are coming from an agency known as the Climate Prediction Center. So if you go to Google and type in CPC, the first hit will be Climate Prediction Center, and you can look for the 3 to 4 week outlook. You can look for the 1 month outlook in temperature and precipitation. These are basically not only dynamical forecasts from models, but they are using statistical analog methods as well. So they are, of course, not as skillful as your day 2 or 3 or 4 forecast, but they are, you could imagine, incredibly beneficial to sectors like energy, which are trying to figure out maybe how much energy demand there might be, agriculture, right? How much rainfall are we going to experience in the next couple of months? Very important for crop yield. And so these forecasts, depending on the sector, can be extremely useful as long as you know how to consume them. You have to be aware of the uncertainty that these forecasts are inherently trying to convey. And I'll end today with just discussing a little bit about improving forecasts. So, one thing that I think will happen over the next 20 to 30 years is our forecast will continue to get better and better and better, but we may hit a very critical point where the advances in computer technology can only take us so far. So, as you're well aware, computer processing and chips and computer processing are getting smaller and smaller and smaller, and so really the number of calculations per second we can do is becoming greater and greater and greater, and no doubt that increases in computer technology are going to be a big component of improving forecasts in the next 20 to 30 years. We're also continuing to do research, so we advance our understanding of the ocean atmosphere system, and in doing so, we uncover new things that allow us to make our models better. But there may be a point in the future where our models are not going to get much better unless we have improvements in our observing network. So this really goes back to the remote sensing discussion that we had earlier in this lecture. In other words, if you put bad data or inadequate data into your model, you're going to get bad results out. And so if you really want to make a model better, you have to improve the data that's going into the models, both in space and time, to be able to make better forecasts. So in order to do that, this is really a three-tiered system. We're doing this really well, we're doing this really well, but one thing that the United States in particular, and I think globally, that we're going to have a discussion about in the next 20 to 30 years, is if we're going to get better forecasts, we must make improvements in our observation networks. We need to launch more weather balloons, we need to have more surface observing sites in order to have better data go into our numerical weather prediction models. You'd be amazed at the amount of data that goes into any given forecast. This is just from one cycle of a model. We bring in surface weather stations and ship data from ships that are going across the Pacific, Atlantic, Indian Oceans, etc. We have buoys that are out in the oceans that are taking data. We launch weather balloons. Pilots are going up and down, taking aircraft measurements as they fly from continent to continent. We have satellite coverage that's trying to get us radiation and scatterometer measurements. All of these data are going into our numerical weather models to try to make a better forecast. And if we can get better at sampling and tailoring these observation networks to bring us better data sets to go into the models, there's no doubt that the forecast that you get at the end of the day is going to be a better forecast if we can put in better data. Okay, so that really brings us to the end of the course, Unit 17 here, weather, remote sensing and forecasting. There's really a lot to forecasting, and we've really only scratched the surface. But you should be able to learn a little bit more by doing the investigations manual or reading through the supplemental PowerPoints.